Is the first VESIcal demo video. And what I'm going to be showing you today is a broad overview of the tool with some tips and tricks inside just to sort of get you started with VESIcal. So what I'm going to be doing today, it's all going to be contained inside this Jupyter notebook. This is my favorite way to interact with VESIcal. So if you're looking for other ways to interact with VESIcal, you'll have to see those other demo videos. But for this one, we'll be using this Jupyter notebook. This notebook file will be available along with the video. So you should be able to grab that file and follow along if you like, either using the data that I'm providing or your own data. So the first thing you want to do in your Jupyter file is import VESIcal so that we can use that library. So import VESIcal as V is my favorite way to do it. And that just means every time we use one of the VESIcal functions, we'll put a V dot in front of that function. And now I'm going to be uploading to VESIcal some melt inclusions, and I'll show you those here. So I have an Excel file with some melt inclusion data from Roggensack 2001 from Cerro Negro volcano. You can see the citation here and here. So this is the paper where these are from. And this is the general way you always want to organize your VESIcal file, where you have each row as a unique sample, oxides as column titles, and some column with sample name information. And that is required because there are ways to interact with VESIcal in which you might want to pull a sample out. And so it's required anytime you upload a file, you have to have a row like this. The default is label with a capital L, but you can change that to anything you like. But for this demo, we'll just be doing it with the default using label. So all right, let's pull these data into VESIcal and calculate a bunch of things for them. So to do that, we're going to create a variable called myFile. You can call this whatever you like. And that is equal to v.excel file, and then the name of our file, which was cerro_negro.xlsx. And there it is. That's important. It's as quick as that. If we want to look at the data to verify that they've been pulled in and see what they look like at any time, we can always do myFile.data, and that will print out our file. So here you go. That's exactly the same data that was in our Excel spreadsheet. Now, for those of you who are familiar with Python, this is a pandas data frame object. So myFile.data can be called as any kind of in any way you call any pandas data frame. So if you're familiar with that, feel free to play around with those tools. For example, if I want to just look at the H2O data, I can do it like that. It gives me all the H2O data. And this is structured such that the index of this data frame is called label. But this is not important to most users. So that's something that if you wish, you can dive into. So great, we've shown what our data looked like. Let's do some stuff with our data. Well, the first question you might have before doing any calculations is, which model should I use? As you may know, MagmaSat, which is the water and CO2 solubility model by Ghiorso and Gualda, which is the solubility model used in melts and rhyolite melts. That is our default model. So if you don't tell VESIcal which model you want to use, it'll use MagmaSat. But you might want to use something else. So what we've coded into VESIcal is a tool for you to help decide. And we can do that by plotting what's called the calib plot, calibration plot, and call that with v.calibplot. And the user data, that's your stuff, is myFile. Hit enter. And what you'll see here is that this warning is because this is still in development. That'll go away as soon as we finish this here. But what you're seeing here is a TAS diagram, total alkali silica diagram, of all of the calibration data used in the various model data sets. Your data is plotted here in the pluses. So those are our Cerro Negro basaltic melt inclusions. And you can immediately see that these gray points, which are for MagmaSat, cover the widest compositional range. But there are a number of models that may work for you in this case. The Iacono-Marziano model here in pink looks pretty good. Some of the more data set will work pretty well for you. But again, MagmaSat is well suited to most compositions and a wide range of pressure and temperatures. So we can go ahead and use that here, or whatever you choose. So this is just a tool to help you decide what model you might want to use. So let's go through each of the 5 core calculations and just see how to do that. So the first one is calculating dissolved volatile concentrations. And for all of these, the next few examples, I'm going to be showing you how to do that for the entire data set. When you're working with a batch calculation, we're always going to be calling back to this my file object. So you've saved this variable and we're going to be calling that a lot. So just remember the name of that. So let's save our calculated data to a new variable called dissolved. And we'll set that equal to my file dot calculate dissolved volatiles. And here you have to give it a temperature, a pressure, and optionally a fluid concentration, fluid composition in H2O CO2. So let's say our temperature is 1100. It seems reasonable for a basalt. Our pressure is 3000 bars, and this is in degrees C, and this is in bars always. And our X fluid is the mole fraction of H2O in the H2O CO2 fluid. And the default here is 1. So if I didn't pass this at all, it would be 1. You could put 0.5, 0, anything you like. Let's just go with 1 for now. And we hit enter. One thing to note here is that MagmaSat is the slowest of all the model calculations. So that's one reason why these things are printing out here by default. This printing will occur. You can set print underscore status to false if you don't want to see that. But I've put it here in this calculation as default on because MagmaSat can be quite slow. The reason for that is that it is completely thermodynamically based, and the way it works is by solving the equilibrium state of the melt phase iteratively, possibly hundreds or thousands of times, depending on how many samples you have. And so that's why this is slower than the other models, which are a single or 1 or 2 or a few equations that are easily solved by the computer. But that's still pretty quick, much quicker than if you'd done it by hand in MagmaSat. So cool, we've created this whole data set. What does it look like? Let's print that. Just type dissolved and hit enter. And this is our data set. So these are all what's returned to you is the original user data. So these are the values that you passed in here, plus the stuff calculated by VESIcal. And those are always denoted with underscore VESIcal. So say in case you had your own H2O values in here, your own temperature values in here, you wouldn't get confused between those. So you can see here for each sample, we've calculated the H2O dissolved in the liquid. There's no CO2 because we set the X fluid to 1. Are the temperature and the pressure that was used that you input into this calculation, 1100 degrees C and 3000 bars. Again, the X fluid input is 1. And the model you used was MagmaSat. We could choose another model here. And in any of these calculations, you can always change whatever model you want. So if we want to do something other than the default, let's look back at our calibration data set. I think the Iacono-Marciano looks pretty decent. So let's go ahead and make a second file, or second data set, rather. Let's call it dissolved Iacono-Marciano. And let's just do the exact same thing, except we will add model equals, in quotes, Iacono-Marciano. And press enter. Actually, yeah, press enter. So this is recalculating. This will show you the difference in speed between the two models. It's recalculating everything in MagmaSat because I ran the cell again. And as soon as it's done, you won't even notice it calculate using the Iacono-Marciano model because it's that fast. So as soon as it appeared that this one was done, both were done because it's just that fast. Every other model is super, super fast. So let's take a look at that data set. So dissolved Iacono-Marciano. Hit enter. And here we are, the same things. And now you see that the model is showing as Iacono-Marciano because that's what we put in. Cool. So that was that easy. We just calculated with 2 different models the dissolved volatile concentrations at a given pressure and temperature for that whole data set. Let's move on to some other core calculations and I can show you some other tips and tricks. So the next one is calculating equilibrium fluid compositions. That is the composition of the fluid, the H2O CO2 fluid in equilibrium with your melt with given H2O and CO2 concentrations, which are defined in your file, and a given pressure and temperature. So let's call that eq fluid. It's essentially the same method that we just did, although the function name is different. So my file dot calculate equilibrium fluid comp temperature. Let's do 1100 again to be consistent, and pressure at 3000 bars. And we hit enter here. That was pretty fast. So that's why this one doesn't print anything out. This just happens to be a much faster calculation. That was in MagmaSat, and we can go ahead and look at the results of that. Here they are. So one interesting thing, since we did the pressure at 3000 bars, a relatively high pressure for this data set. And so you'll notice a lot of these values. So here's your XH2O fluid, XCO2 fluid. A lot of these are coming back as 0 and 0. And that will happen if there is no fluid. In other words, you're not saturated at that pressure. Some of them are saturated at that pressure just. There's some here that are saturated at above 3000 bars. So, let's try that again because we want to see more of these calculated out. Let's try 1000 bars. Probably they'll all be saturated at 1000 bars. Again, this is really fast. So you hit enter and it's done. We hit enter to show this again, and lo and behold, here they all are. Looks like almost every sample was saturated. Now you'll notice a couple of warnings here. So the rightmost column is called warnings. When something goes wrong with a calculation, VESIcal will tell you, and it will try to tell you what happened, what went wrong. Sometimes it can't. So it'll just say calculation failed, and it will return nans, not a number, instead of zeros. So when you get that returned to you, something is wrong. And it might be... So let's just have a look at the data set and see if we can figure out what went wrong. So it's 45 star and 66 star. Was there something weird about those samples? Okay, here's our original data. 45 star. Looks fine. 66 star. So it's not immediately clear to me why these two failed. We could have a closer look into this and then try to figure that out. But for now, for this video, I'm just going to move on. Just to show you that functionality exists, and that's why you'll be seeing those NaN values if you do get them. Cool. All right. Let's do one other of the core calculations, and then we'll get into the final two core calculations, which also have to do with plotting, and that gets really fun, in my opinion, if you're a geek about this like me. So the third core calculation is calculate saturation pressure. So again, same method as above, sat-ps, we're going to call it, equals my file dot calculate saturation pressure. And here, obviously, you don't pass a pressure because that's what you're calculating. All you pass is a temperature. Let's go with 1100 again. And this is another sort of slowish calculation. And so by default, it prints out each sample as it calculates. Again, any other model besides MagmaSat is going to be much quicker. And you just do that by adding model equals right here. But there it is. It's done. Let's take a look at that. Sat-ps. Here are our calculated values. Saturation pressure in bars. And so they're exactly where we would expect them to be. And a lot of them are below 3000 bars, which we expect based on the previous calculations that we ran. One other thing you'll notice here is that we've returned more than just the saturation pressure and the temperature values passed. We've also returned for you the fluid composition in equilibrium with your melting conclusion at saturation. And we've included the fluid mass in grams and the fluid system weight percent, that is the weight percent of the system that is fluid. So if this were 2, that meant 2% of your system is fluid and 98% is liquid. These are very, very small because, of course, in theory, at saturation, this number should be infinitesimally small. But because we can't calculate something that's infinitesimally small, MagmaSat does its best to find the smallest value for the fluid mass. And so, you know, for transparency, because this might be important to you when you're thinking about what these numbers mean, we've reported what that value is. And these are reported to you just because we happened to calculate them along the way, so why not give them to the user? So that's neat. You might see some what we call verbose data returned to you, depending on the calculation that you use. Cool, so those are the three sort of most basic core calculations. Now let's get into some what I think are the most fun things, which are the calculations that also are very good for plotting, because I love our plot function. So the fourth core calculation we're going to do is to calculate isobars and isopleths. Those are lines of constant pressure, curves of constant pressure and curves of constant fluid composition. And it follows the same format as the other calculations did, with an exception that we have not allowed the user to do this for an entire Excel spreadsheet because it seems silly and very, very slow. This calculation does take a long time. It can be done. It will take a couple minutes. I've done it. And I'll give you some clues as to how you might want to do that. But for now, what we're going to do is just grab a single sample out of our data set and run that calculation with that one sample. So to grab a sample out of your data set, you can always use this anytime you want. Let's make a variable called mySample. And the way we grab that is by calling myFile.dot, as always. And there's a function called getSampleOxideComp. You pass the name of the sample, which is in that label column. This is why we require that your samples are passed with some form of label column. And we're going to grab sample 19 star. I like that sample. Let's grab sample 19 star. And let's go ahead and normalize it when we pull it in, just because we can. You don't have to. I could hit enter here, and now I've stored my sample as it is input, and so it'll match exactly the way it looks in your file. But I want to go ahead and normalize it. So let's normalize it in a standard way. And so this value standard, there's a few ways you can standardize, you can normalize, your sample. If I call this something wrong, it will tell us what the options are. So norm must be either none, which is the default, standard, which is take everything and divide it by 100%, fixed volatiles, where you hold the volatiles constant and you normalize everything else, or additional volatiles, where you normalize everything anhydrous to 100% and then adding in the volatiles which make the total more than 100%. And those are used for various functions in VESIcal, and you can use them if you want. But for now, let's just do our standard normalization. If we want to see what that looks like, let's print it out. My sample. This is what your sample looks like. Again, for those of you who know Python, you'll see that this is a dictionary, where the keys are your oxides and the values are the values of the oxides. So you can iterate on this as you would any dict. And just like my data frame, I can say, just give me my H2O value. And there it is. Cool. All right, now let's do some calculating. Let's calculate isobars and isopleths for this sample. And here's how you do that. We're unpacking two variables here. So we save two variables. Let's call them isobars and isopleths. Call them whatever you like. Equals. And now that we're not iterating over this myFile object, we don't need to pass myFile dot. Instead, we pass v dot, VESIcal dot, calculate isobars and isopleths. The sample name is mySample. The temperature, let's do 1100 as we've been doing, keep that consistent. Pressure list. Now, this you pass as a list, which means it has to be in square brackets. And you can give as many pressures as you like. Let's try 2,000, 3,000, and 4,000 bars. Let's specify some isopleths. Same thing as pressure list. It's passed as a list. 0 and 1 are always calculated, so you don't need to pass those, but you can if you want. But let's also calculate them at 0.25, 0.5, and 0.75. And these are in XH2O, in other words, the mole fraction of H2O in the H2O-CO2 fluid. And one other separate thing, one other distinct thing when running these kinds of calculations on single samples is you always need to put dot result at the end. And that's just a function of the way that the code is written. So that what you're getting out of this is the result rather than a calculate object, for those of you who know Python. So let's click enter here. These can be slow or they can be fast. They're usually not the fastest thing. If we want to see that printing, we can always add print status equals true. And we can watch those things being calculated. Oops, but now I see I've made a mistake. So see, you notice here, I'll leave this in because it's a good teaching moment. It only calculated isopleths at 0 and 1 because I spelled this wrong. It should be isopleth list. There we go. I was surprised it was that fast. So there you go. You can see at 2,000 bars, we're doing 0, 0.25, 0.5, 0.75. 1 is always really fast for some reason. It's calculating our 3,000 bar values. So what it's doing here is it's calculating single points that are going to end up on this plot. When we plot them, we're going to be plotting polynomials which are fit to these data. And that's really important to know because if you change these values here, isopleth list, you're changing the data with which VESIcal uses to fit your polynomial. So the more of these you have, the more true to reality your isobars will look in H2O-CO2 space. And we can get a good look of that. Now that this is done, we'll go ahead and plot it up. This is my favorite part. I love our plot function. It's super versatile, and it can handle all kinds of stuff you throw at it, and it can handle these data. You don't even have to think about what these data look like. If you want to, you can. Isobars. Just like everything else, this is a pandas data frame. You can save this, just like everything else, to an Excel file, which I'll show you in a minute. But you don't have to care what this looks like if you just want to plot it. So v.plot isobars equals isobars, isopleths equals isopleths. And it's that fast because matplotlib is super fast. So this is just, again, for those of you who are Python users, this is just using the matplotlib function and telling it exactly how to handle all the data. And you'll see that it automatically labels your data for you to the extent that it can. You can add your own labels if you want. I'll show you how to do that in a minute. So here we have 2,000, 3,000, and 4,000 bars. And the isopleths, we didn't want to report like a bajillion isopleth lines here, so we just grouped them in this one object in the label here. So you can see at which XH2O fluid values your isopleths are plotted. So we have 0, 0.25, 0.5, 0.75, and 1. And so now back to kind of what I was saying about how these are fit polynomials. So the value here at 0 H2O and the value here at XH2O equals 0.75, those are computed values. So everything you see is pretty close to reality. But if there's any weirdness happening, for example, this can happen sometimes at higher pressures and depending on the model you use, et cetera, et cetera. If there's any weirdness happening here, for example, if this should have been fit to a power curve or a third order polynomial, you won't see that here. You will see that if you plot an infinite number of isopleths. But this smoothed data here, so basically, we have distinct points. If I didn't smooth the data, if I didn't fit a polynomial to it, it would look like straight lines. And you can do that. So you can actually calculate the raw data if you want. This is pretty close to reality and probably what you're going to want to use. But of course, this is important. We want people to be able to access this data and use them in the way, the real true to nature way. And so we can do that here by adding another argument. We can tell it smooth isobars equals false. And so now this is going to recalculate all of these isobars and isopleths, but it's not going to calculate the polynomial fits because that actually happens in this step. And as soon as that's done, we can plot it up again. And you can even pass that here. Smooth isobars equals false. Oops. Done. And what you'll get is this spiderweb looking thing. So you can see now how this is the actual data that's calculated. The lines are drawn in between those individual data points. Same thing for the isoplots. Those are automatically smoothed, and we can tell them not to be smoothed if we want to see this data. But you can see that, you know, the polynomial fit is a pretty good fit to these data. And again, this point is constrained. This point is constrained always, even if you don't pass 0 and 1 in the isoplots list, it will calculate it anyway. It won't let you not. So that the pure H2O and pure CO2 values are always computed. And then whatever else you give it is computed. So the more isoplots you have, the better constrained this curve is. If you pass true here, we can see them smoothed again. So we can tell this function to smooth them, but you have to have not smoothed isobars output in the original calculation in order to see them not smoothed in the plot. Let's have a look at a little bit more into the functionality of plot, because I think it's really fun. You can add more than just one calculation to this. You can add a bajillion calculations. So let's show you a little taste of that here. Why don't we go ahead and plot on top of our isobars and isoplots our data point, are the H2O and CO2 concentrations in that melt inclusion 19 star. We can plot any custom XY points. These are always H2O CO2 plots, and so those arguments are called custom H2O, and they're always a list. That means whatever you give to it, even if it's only one item, it has to be surrounded by square brackets. And let's just grab my sample, and let's get only the H2O value from my sample. And then we have custom CO2 equals list my sample CO2. Hit enter. And there it is. There's our first plot and our second plot with our point here. Now you'll see this just shows custom 1. We can give that a label. So let's add custom labels equals. This is always a list as well. Let's call that 19 star. There, and look at that. It shows 19 star. So we could pass a ton of these, and the labels, the first label always corresponds to the first H2O and CO2 point, and so on. I'll show you a little bit more of plot on this next thing. So the final core calculation is to calculate degassing paths. And that's something that maybe we can plot on top of this as well. There are 4 types of degassing paths that you can calculate. You can calculate, and of course, a degassing path, I'll just say, is the path that this melt inclusion or aliquot of melt will take if you just take it as it is and you bring it to the surface. So as you move through pressure space at a constant temperature, it will start to lose CO2 rather rapidly and then start to lose H2O until you get down to its 0 or 1 bar solubility. So we can calculate closed system degassing, in which every time you degas a little bit of fluid, it stays in the system. We can do open system degassing, in which every time you degas a little bit of fluid, the fluid leaves. So you're fractionating the fluid. We can do a partially open system where you're fractionating, say, 50% of the fluid and leaving the rest in contact with your melt. We can also, for closed system degassing, we can also specify an initial fluid that lives in equilibrium with our melt. So maybe we started out in the magma chamber with 2 weight % fluid. You can do that calculation as well, and all those will look different. So let's do each of those. So let's do our closed system degassing first. This is going to be just like isobars and isoplots, v.calculate. Remember, we're only doing this for one sample. Degassing path, sample equals my sample, temperature equals 1000. And don't forget the dot result. Oh, sorry, let's do 1100. We want to stay consistent here, especially if we're going to be plotting it with this guy. So let's do this again. Let's do this 4 times for each of our 4 types of paths. We can calculate. Let's calculate an open system path. Let's calculate a half and half, fractionate 50% of the vapor. And let's calculate dissolved path where we start out with, let's say 2% fluid in the system. And how we do that is we add these extra arguments. Here it's fractionate vapor equals 1. That's completely open system. That means every time we create a little bit of fluid, all of it leaves. We can say fractionate vapor equals 0.5. And we could say fraction, and that's so half of the fluid leaves every time we fractionate. Every time we move to a new pressure step and create some vapor. And here I haven't put that fractionate vapor value. I could say fractionate vapor equals 0, but we don't need to because that's the default. So the default is closed system. And it's the same thing as fractionate vapor equals 0. For the exsolved, this is going to be a closed system because what's the point of starting out with vapor if we're just going to lose it? So we add our init vapor equals, let's say 2.0. So that's 2 weight percent. So that's going to take a second to calculate. It's doing 4 of those calculations in tandem. And so while that gets settled, let's go ahead and get ready to plot this. Let's do our v.plot. Let's plot those isobars again. Let's plot those isopleths again. And then let's go ahead and plot our degassing paths. So degassing paths equals, this is always a list. Closed path, we're going to put all of them on there. Open path, half path. And it's done calculating, by the way. And exsolved path. Okay, and let's give those some labels so we know which is which. Just like we gave a label to our point here, let's say degassing path labels equals, this is always a list, closed, and these should be strings. In other words, they should have double quotes or single quotes around them. Open, half, exsolved. That's it. Now we hit Shift Enter. Just kidding. I forgot to put equals. Put an underscore. Look at that. Teachable moments. And boom. There it is. Remember we had output non-smoothed isobars, but I like them smoothed. So let's smooth them. Smooth isobars equals true. And there we go. Look at all the stuff we just plotted. By default, you'll notice this point is here. That's our 19 star point. That'll always be plotted along with your degassing path. That's why I didn't need to plot it again. I could. It would just be a blue dot on top of there. And so you can see we have our 2,000, 3,000, 4,000 isobars, our isopleths, and all of our degassing paths. So closed, open, half, and exsolved. And those look how they should. The exsolved has the most water in it because you're starting out with this probably pretty water-rich vapor. And then our other types of degassing paths. So you can think about what might be happening to your melt in any situation. So that's where I'm going to leave you at for now. I think this is a pretty good introduction. If you want to learn more, you want to do more with this stuff, check out more of these videos, check out more of our read the docs, or get in touch. We're always happy to add features and help you through anything that you might need to do. If you want to report any issues with the code, you're getting bugs, you're getting weird behavior, please get in touch. Either email us or submit an issue on our GitHub page. So you go to our github.com/kli/VESIcal, go to the issues page and submit a new issue. And please let us know what you're doing and give us the code that you used to generate the error so we can try to replicate that and see if we can fix it for you. So thanks a lot. I hope you enjoyed learning a little bit about VESIcal.